Okay, I think we're all set up. What class is this? 470, okay. So we are going to start talking about amplitude modulation. Nothing but colored chalk. Good. Well, it is the reason we start with it. What do we decide that the lights are better off or on, or is it too bright in here for you to sleep, or we okay? Okay. So amplitude modulation, or AM. And there are a couple of different types of amplitude modulation. We're actually going to start with AM radio, and it's the simplest form of AM. Actually, mathematically, it's not maybe not the simplest, but it allows you to have very inexpensive receivers, and that's why it caught on. You essentially just need a diode to pick up as a radio receiver for AM radio. So it allowed, it was the first mass communication device, right? We had AM radio before we had television, and it allowed, almost everyone to buy an AM receiver because they were so cheap, so inexpensive. So some notation. M of T is the baseband message. Okay, so this would be, the signal coming out of the microphone, or when we get to the video, the signal coming out of the video camera. It's not translated up in frequency. Okay. So for audio, it's typically, for speech, it's below 4 kilohertz. For music, maybe up to 12, 15 kilohertz. But, with, usually there's very little content in speech or music below 50 hertz. That's where your bass is, around 50 hertz, or 50 to 100 hertz. But, it's a low frequency signal. And C of T is what we call the carrier signal. Now the carrier is just a sinusoid. So here I'll represent it as a cosine. That's typically what we use as our reference waveform. And then the different modulation techniques that we look at are somehow, we impose our message on this carrier signal. In amplitude modulation, we change the amplitude of the sinusoid in proportion to our message. And frequency modulation, we actually change the frequency portion. There's another term called phase modulation, where I haven't even put a phase term on there, but where we change the phase in proportion to the message. So the AM radio, mathematically, so S of T represents our AM radio waveform. Mathematically, it's really simple. We just multiply our carrier by this 1 plus KAMT, or that becomes AC 1 plus KAMT times cosine of 2 pi FC of T, where Ka is defined as the amplitude sensitivity. Sensitivity. Looks like a lot of I's, but I think that's right. Sensitivity. We'll usually make the assumption here that our message has a peak value of 1, never exceeds +1 or goes below -1. And we generally assume it has 0 average value. That's typically true, at least for signal coming out of a microphone. Now, again, the signal coming out of a microphone may not have that peak value, but we can scale it or take that into account with a KA. Okay. So we actually will put a restriction on this. This has to be actually less than 1 in peak value, and we'll see why in just a minute. Okay, so there are 2 requirements here for AM radio to work. One is that 1 plus KA MT has to always be greater than 0, can never be negative. And if that's not met, we actually get a distorted signal. Or equivalently, that means KA MT has to be less than 1. Okay, and again, we'll kind of see why in just a minute. And the other requirement is that the carrier frequency is much, much greater than W, where W is the bandwidth of the message. Okay. So again, for an audio signal, if it's just speech, W might be 4 kilohertz. If it's music, W might go up to 12 kilohertz. These carrier frequencies for AM radio, anyone listen to any AM radio stations? You never even go to AM, huh? No one, what, sports radio, nothing like that? Do you even know the frequency or what the numbers that appear on your radio when you accidentally are going from FM to Bluetooth or something and it pops on and you have to go through AM? Yeah, 690, I think it goes up to like 1400, 1440, 1600 actually. But you know what those are, what those numbers are? No, they're kilohertz actually, okay? So it's right about, 660 kilohertz to 1440 kilohertz. That's around a megahertz, okay? So 0.6 to 1.4 megahertz, okay? FM, you're hopefully a little more familiar with. What's a number for an FM radio station? 97.1, okay. You know what those are? Units. Those are megahertz, yeah. So FM, about 100 times the frequency of AM radio. FM's around 100 megahertz. AM radio is around 1 megahertz, okay. And then there's spacing between, what's the spacing between FM radio stations? Yeah, it's 0.2, it's 93.1. The next one, the station would be 93.3, 93.5. So they're 200 megahertz apart. And we'll talk about why that is. It's to make sure that there's no overlap between the signals, okay? And AM, no idea, probably have no idea what the spacing there is, but they're 10 kilohertz apart. So go from 660 to 670 to 680 kilohertz on that. But again, that spacing is directly proportional to W for AM radio. It's a little more complicated for FM, and we'll talk about that. But I want to try and draw some pictures here to give you an idea of what this looks like. We'll look at it in the time domain. It's important to have an understanding of it in the time domain, especially so that you have an understanding of how the AM receiver works. But then we'll also look at what's going on here in the frequency domain. We know that multiplication in time becomes convolution in frequency, right? But fortunately, we're convolving with a cosine, which is an impulse in frequency, so the convolution is pretty simple. So, here's some pictures for, say, the message, maybe it looks like this. And you know, units here would depend on what type of signal it is. So if I've really, you know, zoomed in on an audio signal, you know, this is maybe tenth of a millisecond or something. That would correspond to, you know, a period of 10 kilohertz, a tenth of a millisecond, something like that, or a millisecond for a, you know, if the frequency is around 1 kilohertz. You know, but it's a sum of a bunch of different frequencies, you know, the voice is. So, but this is a small segment of that. The AC 1 plus KAMT, this restriction, so this is really just, you know, I've scaled it, and then I've put a DC offset on it. I've shifted it up. Okay. This restriction that this KAMT term has to be between plus or minus 1 means that the sum has to be between 2 and 0. Right? What it really means is that this 1 plus KAMT, that KA has to be restricted so that that 1 plus KAMT is never negative. Okay. So, and then it's multiplied by AC. So it's really this same picture. You know, it's amplitude scaled, but I'm trying to draw it shifted up here. It's supposed to be the same picture, but just scaled in amplitude and then shifted up. So now this never goes negative. And then what does S of t look like? And that's equal to 1 plus KAMT times AC cosine of 2 pi FC of t. Okay. Now, a good way to at least get a rough sketch of what this looks like, and you can do this with a plotting program, but the cosine, if I sketch the cosine, it is a really high frequency signal. Compared to, you know, any frequencies in my baseband signal. So this is the carrier. And actually on the same time scale, this would appear to be just a solid block here, okay, unless you really zoomed in. Because we're talking about frequencies here in the megahertz range, where here frequencies are, you know, a kilohertz, you know, 1,000 times greater in frequency, or 1/1000th the period. So I haven't even drawn these, you know, if this is a period here, you know, 1/1000th is going to be even compressed more than I've drawn it there. But a good way to try and draw what this product looks like, anytime you have some message times a cosine, is the cosine is just alternating between plus and minus 1 all the time. Okay. So a good way to get an idea of what this looks like is we'll draw this signal again. I'm not doing a very good job. Okay. Now this is what we would get, you know, for multiplying by plus 1. Okay. What would we get if we were multiplying this by minus 1? Well, it would be the negative of this. That's about the best I can do, okay? But just flipping that image about my amplitude equals 0 line. It's a mirror image there. Now, this is called actually the envelope of the signal. What the product would really look like is, you know, this is multiplied by, you know, plus 1, and then it's minus 1, and then plus 1, and then minus 1, right? The actual waveform is going to follow the cosine. You know, when the cosine is 0, this is 0. But what this part is doing is actually changing or modulating. Modulate is just another way synonym for change, is changing or modulating the amplitude of this high frequency cosine. Okay, so, you know, if you zoomed in on this, you wouldn't see this line here that's my message. All you'd see is this cosine, this high frequency cosine, but the amplitude of that is changing. Okay, so this is the actual AM waveform that I'm sketching now. Okay. But if you looked at that, you can say, I still see my low frequency message in there, right? I can kind of see, you know, it's shifted up, but I see it here. I see a representation of that low frequency message. You know, this is what's transmitted. This is actually a high frequency signal. So it's modulated to a different frequency, and we'll talk more about why you need to do that. Again, so we can have different channels is one reason. Another is so we can transmit it out of via an antenna. But we have to go back. Okay. We have to, what we want to recover, the original signal that we need to send to our speaker is this message. Okay, so we've translated it into some sort of high frequency version of it, but we have to recover the envelope, okay, from this high frequency message. Now, the first requirement, if 1 plus Ka mt is not positive for all t, we have what's called envelope distortion. Okay, so in that case, at the very peaks here, actually when we, at this minimum, this will actually go below 0. What that would kind of look like now would be this. Okay, and then the mirror image of that would be I did a bad job here. Okay, that would be the mirror image. Okay, this would be the case where 1 plus KAMT goes negative. Okay, and it's negative during this portion of the waveform. The offset 1 wasn't enough to offset the most negative value here. 1 plus that scaled version of that is still negative. Okay, so again, the AM waveform would look like this. Okay, my AM receiver does what's known as envelope detection, or, you know, we're going to look at a circuit that goes from this back to the message. Okay, but that circuit essentially just, you know, connects the dots here, connects the peaks of the AM waveform. Okay, the problem here is if I connect the peaks, that's the waveform I get, right? If I connect the positive peaks. Okay, and you might say, well, why don't I just follow the negative peaks? Our circuit won't do that. It doesn't, you won't know which is actually correct. We don't really know whether maybe the message really looked like this, okay, and had that positive. Or, you know, maybe in this case, it actually was supposed to go negative, but you don't know that. You don't know what the message looks like. Our circuit will actually follow, it's called an envelope detector. Our circuit will follow the positive peaks. This is a distorted version then of the original message. And so this is called, if this condition is not met, we get envelope distortion. Now, depending on how severe that is, the message may still be intelligible, meaning that you can hear it, but it doesn't sound good. Okay. Actually, one of the exercises I have you do is we'll do a lot of these in MATLAB so that you can hear what these different types of distortion look like. Okay, if you are, not what they look like, what they sound like, what the different types of distortion sound like. And one of them we'll listen to is this envelope distortion. Okay. So this requirement here, that first requirement, the envelope ET is equal to the absolute value of 1 plus KAMT. Okay. And this condition that this is always greater than 1, if that's always positive, we can do away with the absolute value signs, right? The envelope would always be this. Okay. And here, that's not what we want. We would like our envelope to be a shifted version of our message. We still have the DC shift here, but that's easy to remove with a DC blocking capacitor. So that's what it looks like in the time domain to the best of my artistic ability, which is not much, but again, we'll get a chance to see these things on oscilloscopes and in MATLAB. Let's take a look at what happens in the frequency domain. Okay. S of t is AC 1 plus Ka mt cosine of 2 pi fc of t. Or just expanding that out, AC cosine of 2 pi fc of t plus Ka, I left out my AC, mt cosine of 2 pi fc of t. Okay. The corresponding spectrum is, this becomes a pair of impulses. It's just a cosine, right? And actually the impulses, it's in your Fourier transform table. We'd have an impulse at the carrier frequency and at the negative of the carrier frequency. And AC KA2. This becomes MT times cosine. That's multiplication of the time domain. That becomes convolution in the frequency domain. But we're convolving with a pair of impulses. Okay. This is the Fourier transform of the cosine part. So this will become M of F convolved with this. Okay. And I'll draw some pictures here to try and illustrate what's going on. But that gives us MF minus FC plus MF plus FC. Okay. And so that's the mathematical representation. It's important, I'll go back over here in the light. It's important to have a, you know, an understanding of what's happening there, you know, graphically. And really mathematically, this thing to generate this S of t is quite simple, right? I need a function generator that creates a high frequency sinusoid and multiplies that times my message, and I've got AM radio. Okay. Now, hardware multipliers aren't necessarily easy things to build. There are a lot of different circuits that you probably haven't seen in electronics to build them, these modulator circuits, but they're relatively simple. You know, a few diodes. But mathematically, it's quite simple. Just multiply by a cosine. You've got a modulated signal, a high frequency signal. That's all it takes. Let's say M of F looks like this. Okay. Has a bandwidth. Remember, the bandwidth is just the positive frequency part. Now, the Fourier transform of a speech signal is not going to look anything like that. Okay, and we'll look at those, but you know, this is just a convenient, an easy figure for me to draw. Okay, So if this were speech signal, W here would be about 4 kilohertz. Okay. The telephone company assumes that the signals they send over the telephone lines are no higher than 4 kilohertz. So that's why you can't play music over the telephone. It just doesn't sound good at the receiver. All the high frequencies are gone. Okay, so for speech, it's about 4 kilohertz. You know, if you're going to use this for music, you'd need this to go up to about 12 or 15 kilohertz for the bandwidth. Okay. So what does S of F look like? Now, the first part at FC, I've got an impulse of weight AC over 2. Now, again, this is in the frequency domain, and this is not to scale, right? We already said FC is maybe 1,000 times W. So I'd be way down the hall if I went 1,000 times, you know, a couple inches there, right? So this is not to scale. This is a much higher frequency than W here. And then I have another impulse at minus FC. Okay. And then the other part of that just represents the baseband spectrum, M of F, shifted up, centered about FC. Okay. And then I'll have another one shifted there. And again, the height here would actually be AM AC over 2. And was there a question? Okay. So, and this is just a straight translation or shifting. So this frequency would be FC plus W. This would be FC minus W. Okay. Some other terminology that you'll hear is, you know, and when we're dealing with real signals, we do have this symmetry. The spectrum is symmetric. And so you'll have this symmetry about the carrier frequency with AM radio. These are called sidebands. So the terminology, this is the upper sideband, or USB, it is not USB cable, it's upper sideband. Okay. So what do you think the other one's called? It's called Fred. No, it's called the lower sideband. Okay, so the lower sideband. Or LSB. Now, you can kind of see here, you might ask the question, well, those are awfully similar. You know, if I have one, can't I generate the other? And the answer is yes. Okay. So do I need both to transmit both of these? And the answer is no. I only really need to transmit one, the upper sideband or the lower sideband. Those are called single sideband modulation methods, and we'll look at those. Those are more complicated. They require more complicated receivers. But standard AM radio is a double sideband method. It's not called double sideband radio, though, because of the presence of that impulse. That impulse actually is our DC shift, right? That's where that came from. The AC plus the AC times 1 times my cosine gives me those impulses. Those impulses are important because they give me that DC shift that allows me to do envelope detection. Without that DC shift, you know, I get this envelope distortion. I can't use an envelope detector to recover my message. There is a way to recover the message from this, but I can't use an envelope detector. I have to use a more sophisticated receiver. Okay, so this is the basic picture. So, you know, with, I'm going to say, let's say this is AM radio 1200 kilohertz. Okay. And so AM 1200 is transmitting using a carrier frequency of 1200 kilohertz, 1.2 kilohertz. Okay. The next radio station, the next allowed radio station in the area would be at 1210, right? or we've already said they're 10 kilohertz apart. Okay. What would be, with some other message at 1210, let's say it looks like this. It has its impulses here. It looks like that. Okay. How large can W be before I start getting overlap between these two? It could be 5,000, right? Half the spacing between the radio, this could be 5,000, that could be 5,000, but my radio stations are 10 kilohertz apart. Okay. So I'm limited here that my bandwidth can't be more than half my frequency spacing, or half my channel spacing. Actually, AM radio, they did the opposite. They said, we're going to allow transmission to up to about 5 kilohertz, so we can transmit. We have to space our stations 10 kilohertz apart. Okay. So again, inherently in AM, it's not good for music. Okay. Standard AM radio is not good for music because of that 10 kilohertz spacing. They only allow frequencies up to about 5 kilohertz. That's why most of AM now is talk radio. Okay. FM has a much wider bandwidth. Okay, than the frequency spacing is 200 kilohertz there. Now again, FM, we actually have to calculate the bandwidth different for modulated FM than AM. But AM is not good for music. Standard AM radio. And the reason is, nothing inherent about AM. There are some other advantages to FM, but we could certainly broadcast music sounded a lot better on AM radio if we space the stations farther apart. If we space them 20 kilohertz apart, we could broadcast frequencies up to 10 kilohertz. Our music would sound a lot better. This is our transmission bandwidth. BT is 2W. And that is equal to our required channel spacing. Okay, so we're going to be looking at, we'll be primarily comparing these modulation methods based on two criteria. What's their transmission bandwidth? And for standard AM radio, it's twice the bandwidth of the message. Okay. And the other is how much power do they use? Okay, those are the big things. You have to pay for power. And then the transmission bandwidth determines how many radio stations we can put in a particular spectra. For AM radio, we said, it goes from 660 up to 1600. They're 10 kilohertz apart, so that determines how many AM radio stations I can actually have. How many AM radio frequencies I can actually have. Again, radio frequencies are reused, right? You can hear maybe 1200 kilohertz here. You go out to California and there's a 12 kilohertz station. But they don't interfere because geographically they're so far apart. Radio waves die off, the amplitude dies off with distance. So, but you won't find 2 AM radio stations or 2 television stations broadcasting at the same frequency in the same geographical area. Okay, the FCC dictates, what stations, how to, the allocation of frequencies to particular stations. Now, as you're driving down the road, you might be listening to one AM radio station or an FM radio station, and you get near the fringe of the coverage, and then you'll pick up another station that's actually from another city. Okay. Okay, so one of the other things that we'll look at is, this is kind of the test signal case. When we, and this is used not only in the lab, but we'll use it for theoretical comparison of these different modulation techniques, is what's it look like if we transmit just a tone, a pure sinusoid? That's what we call a tone. Now, an audio frequency sinusoid, something like 1 kilohertz or 400 hertz or something like that, something in the audio frequency range. So now we're going to let our message be AM cosine of 2 pi FM of t. Okay, so M of t, yeah, I had a cosine there. M of t is a cosine with an amplitude AM. In the frequency domain, I get AM over 2. This is the spectrum of our low frequency tone. Okay, and S of t is AC 1 plus KA, now AM cosine of 2 pi FMT, all times cosine of 2 pi FCT. Okay. Or I can write that as 1 plus mu cosine of 2 pi FMT cosine of 2 pi FCT, okay, where mu is defined as the modulation index, or some books call it the modulation factor. Okay. If we define A max to be AC times 1 plus mu, okay. Remember, this cosine also can go between plus minus 1. So the peak value here is 1 plus mu. So if you were looking at the modulated waveform, what you would have now is actually this cosine signal here, right? Like this is the low frequency tone, and then the high frequency, and then this AC times 1 plus mu is going to be A max, and then this value we'll call it A min. Okay, A-M-I-N, subscript M-I-N. So the minimum value in the envelope is AC times 1 minus mu. That's when cosine is -1. Okay. Now, why are we doing this? Well, it's easy to look on an oscilloscope and figure out what A max and A min are. You'll do this on one of your labs, actually. You'll have to look at the modulated waveform and figure out what the max and min are, and then calculate the modulation index. Mu is A max minus A min over A max plus A min. You can solve those two equations for mu. That's where that comes from. Okay. Just take the ratio. AC disappears. That's why AC is not in this equation. And then solve for mu. I'm not going to go through the steps, but we require mu less than 1, or often the modulation index is given as a percentage. In typical AM radio stations, we'll use modulation indexes of about 0.7. Okay. Okay, so one final thing is on power here. So cosine alpha, cosine beta, and I think I said this will be showing up a lot, is actually cosine of the sum 1/2 cosine of the sum plus 1/2 cosine of the difference. So that means S of t here for tone modulation. If I expand all this out, I've got the AC cosine of 2 pi FCT term, and then I'm going to have the product of these cosines. So that becomes AC mu over 2 cosine of the difference. So that's 2 pi FC minus FM times T. This is actually the carrier term, which contributes an impulse. This is actually the lower sideband term. There's another term that appears here. So now what I'll have, what my AM radio waveform would look like is at FC, I've got these two impulses due to these pair that get modulated up, and then I get the other impulse due to my carrier. Okay, so now I have plus AC mu over 2 cosine of the sum of the two frequencies. But I know how to calculate the power of a cosine signal. Okay, and this allows me to calculate the power of each term. How do you calculate the power from the amplitude of a cosine? Cosine of 10 volt peak. It's the RMS value squared. Right? How do you get the RMS value from the peak value? I know it's been a while since you had circuits too. Divide by square root of 2, right? So if it's 10 cosine, the RMS would be 10 divided by square root of 2. Square that, it's 10 squared over 2, right? So the power is actually AC squared over 2 due to this term. And then the lower sideband and upper sideband have the same power. That's the power in this term. And that's going to be the amplitude squared, AC squared mu squared over, but here the amplitude has a 2 in it, so I square that and get 4, and then double it again because of the RMS, and so I get 8. Okay. The power efficiency is defined as the sideband power over the total power. PC plus P LSB plus P USB. Unfortunately, you know, if you plug in terms of mu, you'll get mu squared, all the ACs cancel, you get mu squared over mu squared plus 2. Okay. If you take the limit where mu is at its largest value, this becomes 1/3. So the maximum efficiency of AM radio is 1/3. What it's really measuring is how much power is in your message, right? My sidebands, I erased that picture. Here it is. My sidebands have all my information. This impulse, you know, I don't really need it. It's not in my baseband signal. I need to recover my sidebands. Okay. So in a sense, that impulse, I'd like to get rid of it because it takes a lot of power to transmit it. Okay. As a matter of fact, 2/3 of the total power is actually in that impulse, but that carries no information. Only 1/3 of the power is in the sidebands, which is where all my message information is. So AM is not efficient. Okay. That impulse, though, again, allows me, as we'll see next time, it allows me to have a very simple receiver. Now, who pays for that power? Well, it's the radio station. This is transmitted power. Ultimately, it's you, or it's rather the advertisers that pay the radio station, but they're the ones that are ultimately paying the power bill. But AM radio it allows us to use a really inexpensive receiver but there's a lot of inefficiency in terms of how much power is transmitted with AM radio. And we'll see that other techniques, variants of AM, you know, a couple things. Well, if we get rid of that, if we get rid of this impulse, and we can, it's called double sideband radio, but now our radio becomes much more expensive, on the order of $100 as opposed to a couple dollars, okay? Or the other thing that we can do is actually maybe only transmit one sideband. Again, our radio receiver is much more complex in that case. The presence of this impulse does that shifting, allows me to use a simple envelope detector. And that's why AM radio caught on, because people could afford to buy the little cheap $5 radios, okay, as opposed to going out and spending hundreds or thousands of dollars on a more sophisticated modulation scheme. All right, that is it for today. We'll talk about this more next time on Friday. I may have, I'd have to look. Okay, yeah. Tomorrow is better. I'm free almost all day tomorrow. So Tuesdays and Thursdays are my better days. I've got 2 more classes today, but you can stop in. If I'm not busy at 1, I'll be glad to help you. If I am, I'll run you away. So, yep. Thank you. I'm still recording here, I think. No, you're fine.